let me go through that first, right? Can you all see the overhead? Every one of you, including those in the back. So what's this first equation? You have to think. It's continuity, right? Including a steady term. So this is what you start. So in the exam or in the test, the first thing you do before you write your name down on the question sheet, on every problem you should spell out continuity. Because then I have no choice but to give you credit. Right? No joke. Because some of you will forget to use it. What is the second equation? Momentum in what direction? In x direction. Now, we haven't covered the unsteady term yet. We'll deal with that later. And all the problems you will have for homework, as well as in the test for momentum, will be steady. All right? Do you understand all the terms for both equations? Okay. So step one, what should we do? Answers on the board, you can read it with. You define the control volume. And it's not unique. And this problem, the utility plate will be shown. You can have multiple choices. And turns out the wrong choice can cost you a lot more time, while the answer remains the same. Okay? Second step. Coordinate, x and y. Once again, how you choose to coordinate, by example of this 2D plate problem, can play a role in how long it takes to get to the answer. Answer won't change. I have convinced you of that, right? But it can take you an additional hour of algebra by having the wrong coordinate system. So how do you know which one to choose? Well, by experience. Meaning you have to do the homework. And the more you do it, the more you're familiar with each problem, how to deal with it. Step 3 is, the way I suggest you to do it is divide and conquer. Divide meaning one step at a time. For the momentum equation, deal with the left-hand side. Just write down all the forces. Each of the 3 categories has to be dealt with. Some are negligible, some are not. But you do it separately. Do it left-hand side. And make sure the sign is consistent with your coordinate system. Question on that? Step 4, then, is the resultant forces. Sorry, step 5 is where you can make a lot of mistakes. And that's why I want you to separate them. In that you're dealing with the momentum flux out. If there are more than one entry port, you have to deal with them multiple times. Minus, always minus the momentum flux coming in. And that's where now the m dot, should you care about the sign? Does it have direction? Come to confuse you. What about the velocity u? Same thing, you have to deal with that. And that's why I want to separate them into step 4 and 5. Then you check the sign again in step 6. Make sure you are consistent with the sign with the coordinates. Then step 7 is easy. Now you're done with being an engineer. The rest is accounting. Right, now you put it back in the equation. And step 8 is the one I keep emphasizing you may forget to use, which is continuity. Allow you to eliminate usually a velocity. Step 9, which is not always useful, but for the plate problem is intuitive. Sometimes can the symmetry be used to help solve the problem? And we have used that in some cases for the 1D momentum equation. So let me stop here and make sure you understand all these logical steps. One at a time. Everyone's good, right? This is nothing new. Nothing new, I think. So now let's do a deep dive into this momentum equation of x and y. So I would say at the outset, if you can do this without any help, you deserve an A in this class. Yes?
Are you putting that last sheet online?
I thought it's been posted. It's on campus. You have to check campus, right? So it's been posted 2 lectures ago, I think. And you should have it ready before you come in. Okay, so problem statement. I have a two-dimensional plate, and that should plate, and you should visualize and tell me what it should look like. A jet could be air, could be water. It's not important. Heating an inclined plate. So the first in-class problem I did was a plate that's vertical. Now I put an angle to it. And you are told that constant density, pressure everywhere, including inside the jet. Why is that? It's an open jet, it's atmospheric everywhere. And that's a condition we have used for many times. Steady problem, so no unsteady term. You can neglect gravity, so if it's water, the weight of the water is inconsequential. No friction, inviscid, frictionless. Shear stress is zero. There are four unknown you're asked to look for. As the jet hit the plate, its speed one go up, another stream go down. You're asked to find the height h2 and h3 of that split stream. And in addition, you're asked to find the reaction force Rh and Ry, or in terms of nomenclature, the height of the jet coming out at nozzle 1, velocity, density, and the angle theta of the plate. That's the problem statement. You got it? You understand the geometry? You understand that's different than a axisymmetric jet, right? Any question on that detail? So take a big picture look, 30,000 feet looking down. How many unknowns you're asked to solve for? How many unknowns you're asked to solve for? Four. Which four? Well, there are four listed. Right, two H's, two reaction force. How many equations you need to solve for four unknowns? Four. Name me three. Continuity, very good. In that order, I want to hear the first and foremost, continuity. What else? Momentum in X, momentum in Y. I'm missing one. I'm missing one. This is where, if you can do this problem, you deserve an A. What does it mean to you that the flow is frictionless, inviscid? Rx is zero. Rx is zero. Okay, so I have asked you to revisit 2124, right? And in all the session, you've been told what is a viscosity and how is that being defined. Am I correct? So read that. So next time I give you a quiz, I want you to tell me why, if it's frictionless, the shear is zero. The answer is correct, but I want you to tell me why. Okay, so be aware of that. Okay, so the fourth equation then is recognizing if there's no friction, there's no retarding force on the plate to slow down the fluid flow, then the force along the plate, which is Rx, is zero. We will come back next time and we examine what is the definition of viscosity and how is the shear related to that. And that's your review for 2124. Okay, so using the procedure I established, which is step 1 to 7, the first step is to define control volume, right? The answer is given on the test, on this paper here. But there are two other choices of control volume. I call this A. The other choice will be, like we normally do, draw a rectangle. Right? I call it B. C, we will take this triangle, take this rectangle, rather. And rotate it so it's parallel to the plate. Which one will you pick? First of all, it doesn't matter. Answer won't change. But it does matter, it turns out, by choosing a different control volume, you're adding a lot more work to your algebra. Can someone tell me why I choose A? I mean, the answer is obvious. A, because it's what is on the handout. Why is A click? Why would you think A is better? Yes?
The interfaces are perpendicular to the surfaces given.
By choosing A at all the control surfaces at station 1, 2, and 3, 1, 2, and 3, what is the relationship between the velocity and the area? And all three faces. They're perpendicular. So how would that simplify my use of what equation? The continuity equation. Okay? So by choice, I'm picking this control volume A so that I can take advantage of the fact velocity and area at all stations 1, 2, and 3 are all perpendicular to each other. You see it? Okay. Step 2, coordinate. I give you two choices. Left and right. Which one? Why? Why? Anyone else? Why? Yeah.
That's for the direction of our reaction forces are going in. We're adjusting our axes to go in the same directions that the resultant forces are going in.
Yeah, you choose your axis so that they're parallel to the two unknown Rx, Ry. And the key and the hint is the fact to recognize Rx along the plane is 0 because it's frictionless. How much you think more work will be added if you choose the right-hand side control coordinate? A lot, more than an hour. So on page 3 of this 4-page handout is a very detailed algebraic solution to this same problem, but using this coordinate. And you will find that the algebra is horrendous. Okay? It's a lot more work. Answer doesn't change at the end, but it's a lot more work. Yes?
Is that just a factor of having to find components for every single force?
That's absolutely correct. Yeah, you got it. You got it. Not only it's a lot more work, it's very